Hello, welcome back to EDU 8307. We are going to start now talking about sampling distributions because when we start testing our null hypotheses, the results or the conclusions we come to are going to be based on this idea of a sampling distribution. I will tell you that a discussion of sampling distributions is probably the most theoretical that we'll get to in this course or in a lot of statistics courses, because we have to do a lot of relying on what these statisticians are telling us. Okay, so just kind of bear with me through this. We're going to do an activity at the end that I hope will help make it a little more concrete and less theoretical. So first, let's just think about samples and population. I may have said this before, but I just want to go over it again, the difference between a population and a sample. When I first kind of got into this world of research and someone would say population, my mind automatically went to like the census. What's the population? You know, the giant group of whoever, whatever country you're in. But in research design, we talk about the population in terms of whoever you care about. So, for example, if my study is investigating ninth grade students in urban school districts in Texas, that's my population. From that population of ninth grade students in urban districts in Texas, then I could pull a sample from that population. If I care about incoming freshmen to four-year private universities, that's my population, and I will then pull a sample from that population. Okay, so it's not everybody in the whole wide world, it is specific to that group you care about. If you're having trouble trying to think of what the population is for your study, think about who do you want to be able to apply your findings to. You know, what group is going to be most helped by your findings. You know, if you're doing a study of a treatment for dyslexia, your population is, first of all, students identified as having dyslexia, but then are there other parameters like male students between the ages of 7 and 11? You know, whatever you're going to find with your study, who do you want it to be able to almost reflect back on, or find your results useful? Okay, so that's your population. And then you're going to pull a sample from your identified population. Okay, so when we talk about statistics, we're automatically talking about samples. If we're talking about a population, then we'll talk in terms of parameters. And there are even different symbols depending on whether or not you're talking about a sample statistic or a population parameter. So the mean symbol, we've been using that quite a bit so far. But if it's the average of the population or the mean of the population, we switch to another symbol, and that's our mu symbol. Standard deviation changes, whether it's a statistic or a parameter. Variance changes. Pearson R, proportion changes, depending on if we're talking about the sample statistic or the population parameter. And just thinking about practical terms, the population parameters a lot of times are not known. There are more limited situations where we actually know, say, the mean of the population on some characteristic. And if we did know the mean of the population, there's probably not a reason to draw a sample, because if you have identified everybody and measured everybody on a particular characteristic, then why would you want to pull a sample? See what I mean? A lot of times we pull samples because we're not able to identify and measure everyone in the population. So we pull a sample that we hope represents the population. Okay? When you think about sampling, we hear a lot about random sampling. And in fact, a lot of the statistics or analyses that we do depend on random random sampling. In the next course, 8304, we'll talk about assumptions of our different analyses, and a lot of the analyses we go through have this assumption of random sampling. So random sampling is, look at that second point there, it's a sample drawn from a population such that each possible sample of the specified size has an equal probability of being selected. All right, so let me kind of give you an idea of how difficult true random sampling is. In order for a sample to be truly random, a researcher has to be able to identify and have available for selection every member of a particular population. Well, in some cases that's just not practical, and it may be impossible, as a matter of fact. So if I want to randomly sample 4th grade students in Texas, I might be able to get a list of all the 4th grade students in Texas, but it's going to be pretty tricky. So even if I feel like I'm randomly selecting my participants, a lot of times it's not truly a random sample because it's just so hard to do. So we have some other options. Oops, sorry about that. Let's look here. Random sampling is best, but not always possible. So we could do something like systematic sampling, where we select every nth person. So you might have a list of most of your population, and you could go through and select, say, every 100th person or 10th person, or so on. A stratified random sampling, randomly sampling from specific groups. I had a student who did a reading intervention one summer, and she wanted to make sure that her participants mirrored the community in which she was providing the intervention. And so she determined the population of students in her particular age group who went to a higher SES public school, a Title I public school, a charter school, private school or homeschool, and there was another group there. She figured out within, say, a 10-mile radius of where she was conducting the intervention, those percentages of the percentages of those groups that made up her area, her participant of interest, and she selected randomly according to those percentages, because, like I said, she wanted her participants to represent accurately the area in which she was providing the intervention. Convenient sampling, those are just what we have available. And it's not that convenient samples are necessarily bad, because sometimes you get to the point of this is what I have access to, and I want to investigate this topic, so even though it's not best case scenario, I'm going to go ahead and run my investigation. But what you'd want to do as a researcher is provide a detailed description of the sample, so that a person reading your study, say you had to use an intact group of preschool students from a suburb, and so you might assume they're all, middle to slightly upper middle SES. You would want to describe the area, the backgrounds as much as you could in terms of just generally speaking, of course, not child by child or anything. But you would do this in order for someone else to read your study, could get an idea of, oh, okay, well, that intervention worked for that group, that type of student, and then they could decide, is it worth trying with, maybe they have a totally different group of similarly aged students that they want to try the intervention on, but that way they'll be aware of who your sample was or who this intervention was successful with. Now that we've kind of thought a little bit about sampling, let's talk about this idea of a sampling distribution of means. So now, instead of drawing one sample, so say I am interested in the preschool students in the United States, and I pull a sample, not necessarily a random sample, but it's as random as possible, I guess you could say. I did as good a job as I could pulling the sample. And I calculated the mean score for these preschool students on kindergarten readiness. All right, a sampling distribution of means says that if I were to infinitely sample the preschool students, assess their kindergarten readiness, obtain the mean score for each sample, and then plotted all those means, then I would have not one mean, I would have a sampling distribution of means. Okay? And the idea here is, so this is the theoretical part, because of course we cannot sample an infinite number of times, right? Calculate the mean each time, put all the sample means into a frequency distribution, and have this sampling distribution of means. That's just not practical. We can't do it. But if we could, those plotted means would resemble a normal distribution. But it would be a distribution of means, not scores. Okay, so think about what we've done so far is we have, let's see if I can get my pen to work. There it goes. We have thought about distributions, and we've thought about them in terms of scores. So I've drawn a distribution for you many times like this, but what was under the curve was, say, this is, I'm going to use a little not terminology, but a little notation here. So this is sample 1, and maybe the mean kindergarten readiness score was 62. Okay. All right. Well, before, I wouldn't just plot the mean, would I? I would plot all those scores. So everything under here, those are individual scores from my preschoolers, right? Those are all those kindergarten readiness scores. The difference with this is we're not plotting individual scores. We're going to start plotting those means. So I'm going to pull one sample, and maybe this is 60 here in the middle. All right, I'm going to pull one sample, and then I'm going to plot that mean. And then I'm going to pull another sample of that same size. So this is going to be mean 2. And maybe that mean came out to be 58. And then I'm going to pull sample 3. And maybe that one was 61. I'm going to pull sample 4. Maybe that mean was 70. All right. Now I'm not plotting the individual scores. I'm plotting those means. There's my 58, there's my 61, maybe my 70 is over here, and I would keep doing that. I'm going to call that I, and then you say all the way to infinity. I'm going to keep doing that because theoretically that's what a sampling distribution of means is. It's what would happen if we were to sample an infinite number of times. What would that distribution look like? Well, the idea here is if you plotted all of them, this distribution would resemble a normal distribution. But again, it's a distribution of means, not scores, as we were talking about before. Okay? All right, that sampling distribution of means is a probability distribution. So it's the relative frequency distribution of means obtained from an unlimited series of sampling experiments. Now, all of these unlimited sampling experiments are all of the same sample size. Okay? If we took all that unlimited number or infinite number of samples, calculated the mean, plotted the means, we would get the probability distribution for that particular sample size. All right, so there are probability distributions or sampling distributions for every size sample. All right, so maybe your sample size is 25. So for the sample size 25 of these preschoolers, whatever theoretical sampling distribution there is for that, it's specific to this sample size. So guess what? There's another one for sample size of 26. You can see why all this is theoretical, because we could never do this, right? There's another one for 27, 28, 29, and so on and so on. So it's really a family of distributions related to whatever the characteristic is. In this case, kindergarten readiness. Okay. Here I just made a note. We can't actually create a sampling distribution of means because that would require random sampling an infinite number of times. But mathematicians have derived the characteristics of sampling distribution of means, such as the mean, standard deviation, the shape, which is our skewness and kurtosis. So this allows us, because the mathematicians have done this for us, it allows us to answer our question, what kinds of sample results are likely to be obtained as a result of random sampling variation or chance? Okay, we'll talk more about that as we go along. All right, now the characteristics of those sampling distribution of means we know those, all right? If you repeatedly sampled from the population, calculate the means, plot the means to create a sampling distribution of means, the mean of the sampling distribution, or the mean of your means, will be the population mean. Okay, so if we could randomly sample an infinite number of times and plotted all those means, the mean of the means would be equal to whatever is true in the population. Okay, so we know the mean, the characteristic of a sampling distribution, the mean of the means equals a population mean. That's super confusing. We also have an idea about the standard deviation. So the standard deviation of a sampling distribution, of course they changed the name on you. It's known as the standard error. And it reflects the amount of variability among the sample means. All right, so, and I made some notes here. If you look at the standard error of the mean formula, and think about this, you may have to come back to this and think about it. But the larger the population variance or variability, the more standard error, okay? And if you kind of mull that over for a minute, what it's saying is the larger the population variability, so if you're sampling from a population that is really spread out, high variability, the standard error of your sampling distribution will also be spread out. As you pull a larger sample size, the standard error will become smaller. So the standard deviation of your means, or the standard error, will become smaller the larger and larger the sample size you pull. Okay. We also know the shape of the distribution of sampling means is going to be normal. So those skewness and kurtosis values are going to be right around 0. The central limit theorem tells us that a sampling distribution of means tends toward a normal shape as the sample size increases, regardless of the distributional shape of the population. And so if you've completed one of the assignments using the virtual stats lab, you've had an opportunity to kind of see this in play or in practice, or in a simulation, I should say. Regardless of what that parent population looks like, if you sample enough times from it, your sampling distribution of means will take on the characteristics of a normal distribution. Okay. Central limit theorem, of course, is very important because it allows us to talk in terms of the probability or the probability distribution under a wide variety of sample sizes. Okay, it provides, I think I've said these already. To kind of talk more about this, I want to do an activity using this Rossmann Chance applet. Now in class we do this activity with actual Reese's Pieces. Of course I can't do that with you guys over the web, so let me kind of explain this a little bit. Think about a bag of Reese's Pieces candy. What color candies are in that bag? You have orange, yellow, and brown. Well, the makers of Reese's Pieces actually put in half the pieces should be orange. Okay, that's what the makers say. So the probability of getting an orange should be about 50%. All right, so this is our population information. We know that of all the Reese's Pieces bags in the world, half of the pieces are orange. Now, when they're in the factory and they're filling those bags, you can kind of think of those as your samples. Not every sample is going to be 0.5 right on the money, right? And that's just like when we pull a sample of participants, we are not going to pull, most of the time anyway, we're not going to pull an exact replica of what's going on in the population. So when I'm pulling my sample of preschool kids, it's pretty likely that those preschool kids are not going to perfectly reflect the population from which they're pulled, right? Now, theoretically, random sampling should take care of that, and it should be a pretty close estimation of what's going on in the population. But because of sampling variation and sampling error, our samples are just not going to represent the population to a T. Okay, so this is just a little demonstration of that. So our population information, we know that 50% of the candies are orange. Well, pretend like this is the population. Now I'm going to pull a sample size of 25 from my population, and let's see how many orange we get. In fact, I want to change it to the proportion so that I can get a probability. All right, so I'm going to draw a sample. Let's see how it comes out. All right, so here's my obtained probability. 0.56. Well, see there, it did not perfectly represent the population. My sample is pretty close. And let me scroll down a little bit. And what it does, it plots it for you. So this is going to become our sampling distribution of means. Okay? Or in this case, it's actually the probability or the proportion of orange. It's not a sampling distribution of means, but it is a sampling distribution of the proportion of orange. Okay, so let's draw another one. Let's see what we get this time. 0.6. We're even further away from the population mean. So if this was our research, that might be kind of a kooky sample because that's a 10% difference, right? 0.5 to 0.6. All right, let's draw another sample. 0.36. Whoa, that one's off too. Let's draw another one. 0.52. That's close as we've come. 0.5 is the population value. Our sample is a little bit off from the actual population. So if this was our study, we'd be happy with this. Now, the thing there is, like I said before, we don't usually know this information. So statistical inference, statistical significance testing gives us a way to kind of judge the accuracy of our result. Okay, but for this is just kind of an illustration of how sampling distribution of means or of proportion of orange works. So got another 0.6. All right, I'm going to speed up the process here. I'm going to take 100 samples, size 25. I'm not going to animate it anymore. And it's going to plot it's going to do what we just did, but it's going to do 100 times instead of just the one time. And it's going to plot it for us. So let's see. There you go. There's the 100. Let's do 100 more. 100 more. 100 more. 100 more. What's happening there? It's starting to look what? Normal, like a normal distribution. Now, be careful when it shrinks down like that. It's just the scale has changed over here. Okay, because the total number of samples has gotten bigger. All right, 100, 705. Let's do 100 more, 100 more, 100 more, 100 more, 100 more. Look at that. It looks really cool. Looks pretty normal, right? So as we sample an infinite number of times and plot our result, we're getting that normal distribution, just like the notes on the PowerPoint said earlier. All right, but this way you can kind of see it. So I encourage you to come back and just play with this. If you just type into Google this rossmannchance.com, it'll bring you to, you'll find a link really quickly to this applet collection, and the Reese's Pieces is over here. All right, so there are a lot of resources here, but the Reese's Pieces is a pretty fun one to do when we talk about sampling distributions. Okay.